Hey everyone, I'm Helge, and I'm going to be giving this presentation now, which is titled "Using Synthetic Data for Training of Computer Vision." So just a little bit of a disclaimer before I start. We had hoped to be a bit further with our work on using synthetic data before this talk. What I'll be presenting is sort of our preliminary results. It's not quite at the level where it's published research like some of the other results, but yeah, I still hope you find the application and use case interesting, and yeah, that you get a little bit of an idea of what we're doing with synthetic data, and how maybe you can use it as well. Great. So just a little bit in terms of the agenda for what I'm going to be talking about. So I'm first gonna tell you a little bit about myself, and then a little bit about our startup company called Spore, which does environmental monitoring for renewable energy. So that's a pretty interesting space. I'll share a little bit about sort of the problem that we're trying to solve and why we're trying to solve it. And before I get to the part of synthetic data, I want to just give a bit of an introduction to sort of computer vision in general and computer vision models, and what people have tried before, and what's worked and what hasn't, and so on. And then I'll talk about how we went about generating some synthetic data for our use case, and what kind of results we got when trying to train our computer vision model with that. And then finally, I'll have a bit of a conclusion, what we're thinking of doing next, and share with you some of my contact details if you would like to get in touch after the call. Cool. Sure, let's get started. So about myself, I've been working in sort of the field of machine learning and AI for quite a number of years now, actually. My background is in applied mathematics and computer science. So I did a master's over 10 years ago now, where we were trying to do speech recognition, but from video instead of audio. So kind of like some people are able to read lips. We did that, trying to teach machines to do the same thing, which was very interesting. I then worked briefly in the sort of medical imaging field, did a little bit of things there, but then I guess like a lot of people, follow the money, and since then I've worked quite a number of years in with data science applications in banking, insurance, online marketplaces, and amongst other places. So which was very interesting. Last year, I moved back to Norway after a sort of extended stay abroad. I wasn't super interested in finding a job at the time, rather wanted to start a company at that point. So I joined a program called Antler. If you haven't heard about it, it's their philosophy is that there's a lot of great people out there working at company who want to start companies, but don't know quite how to do it, or don't have anyone to do it, start a company with. So they bring people together. We were a cohort about 50, and set you up to kind of meet each other, get to know each other, work on problems together, and find out who you work well with. And then they also may invest in you after that program. So that's kind of what they provide. So I went through that program. I found two co-founders there. One is Ask, who has a background in Bologna, and Lorea, who work for the UN, which I'll think you'll see why that's relevant for our application once I start talking about that. I also wanted to do something like related to AI again, and also something in renewables. I thought that was a very interesting space, especially in Norway, and what's happening now with the green shift and in the EU and so forth. So we were kind of coming together around that and wanting to find interesting cases to apply AI technology in driving forward and helping the sort of green shift and renewable technology. So that was pretty much our starting point and the background for the company that we decided to call Spore. So if you ever been involved in starting an AI or machine learning company, usually the way it goes is that you go and speak to potential customers in that segment that you're looking for, or looking at rather. So and then you kind of tell them what AI can do. This is computer vision, this is NLP, and so on. And maybe you have some interesting problems, and you maybe do some workshops around that, and come up with some interesting ideas. So we did exactly that. We spoke to quite a number of companies that are either in renewables or have ambitions to get into renewables, and we kind of came up with a short list of problems that we thought could be interesting for this. We looked at everything around maintenance to predicting energy usage, prices, and also the idea that we ended up working with, which turned out to be around the monitoring of the environment in relation to renewable energy. So I'll explain what that is about. We decided eventually to start in the wind energy industry. So the reason for that was, well, I guess a little bit by chance, but we spoke to some of the customers in that segment that were also partners in the Antler program, and they said that this was a very interesting thing. We all, if you've been reading the news, you probably followed the sort of debate around wind in Norway, and a lot of people don't like it, and a lot of well, not liking something is not a great argument often for something not shouldn't exist. So the environmental concerns are often what's being raised as being the problem. So I guess one of the reasons, well, one of the things that's come from that is that the next sort of phase of wind energy is happening offshore. So it's kind of moving offshore, and also by doing that, we can leverage a lot of the expertise that Norway has in offshore technology and infrastructure in the North Sea and so forth. So whenever you want to build such a wind farm, you need to apply for a license to do that. And as part of that, you need to do some sort of monitoring program for biodiversity. So when we're talking about wind energy, we're typically talking about then bird life. And what they told us is that the way that this is being done today is very expensive, very error prone, and not necessarily very accurate. So this example of a person that's flying around in his little plane over an area where they're planning to build a wind farm, and he's talking about and he's recording what he sees. So we saw a kind of opportunity here with what we have now of modern technology and AI to address this problem in a better way. And we also see kind of monitoring of biodiversity in terms of more of the bigger picture as being a sort of next wave that's coming. We already see it in things like ECG investing and EU taxonomy, where companies that can demonstrate that they are environmentally friendly on various factors can get access to more affordable capital and so on. So that's that. There's also a big push towards more renewable energy happening at the moment, and we also have recent improvements in the AI and machine learning technology, and the cost of sensors that we need to use these dropping quite drastically. So kind of with all these things combined, we saw that opportunity, and we went for that. So what we sort of envision, so this will be a typical offshore wind farm. What we want to do is put cameras on the turbines and process that camera data and do the compute then on the side using edge computing. So that's kind of how we envision our system. A question we often get is what do you do before the windmills are there, because you need to do the environmental assessment before you build the wind park. So that's something we're still looking into, but there are a few options there. Like one of the things that we are considering is using something called buoys. So there's the way to assess actually the wind conditions on the site these days is using buoys, and then they use a LiDAR-based technology to actually get a very accurate estimate of the wind. So that's something we can also piggyback on. And of course, in that case, the connection wouldn't be that great. So hence the need to use some form of edge computing so that we can reduce the data a lot before we actually capture it. All right, so this is one of our first kind of models. We did this pretty quickly in the beginning, and it's a YOLA model, which you probably have heard about. It's detecting then birds against blue sky. So this is not the hardest problem. The one we're facing is a lot more difficult. I'll show you a bit more about why just now. But you can see it's finding the birds with drawing bounding boxes surrounding, identify the right type of object, and also gives you a confidence of what it does. Eventually, what we want to build is like a product that give operators of these wind farms a sort of a 360 insight into the actual environmental impact of the wind farm, with all the data they need for reporting, and also to help them take any remedial action that they might want to take. Cool. So we have started. We have one existing project that's running at the moment, and then we have two in the pipeline. So our first one we've done on land. Slightly easier to do the install there. The next one will be offshore, but this is a photo of our little camera that we mounted there on the farm, and it does monitoring of that wind farm. So this is a wind farm on the west coast of Norway. This is actually not our equipment. Just to give you an idea, this is the day we actually installed our system. Our system is that little camera. The rest of the equipment actually belongs to Nano, which is the Norwegian nature science research something, and they actually also put up a radar. So that's very interesting for us. It's a 3D bird radar, very advanced. So it actually allows us to compare the data we get from our computer vision system against the actual data from the radar. So that's going to be very interesting once that's ready. And there is our little system inside the little car there, and this is how AI looks in production. But we're using a NVIDIA Jetson Nano, which is that little box there. So that's our edge computer. It's processing the feed then from the camera and doing the image analysis in real time there. And then we also have the keyboard and screen and stuff if we need to use that. So that's just interesting. So this is the data we're actually getting there. So we have lots and lots of this sort of thing, turning wind turbines. This is a good weather day. It doesn't always look like this. Like the day we installed, there was a snowstorm, so then it's very hard to see anything. But on a day like this, we can see quite a bit. So our task is then to detect any birds that are in here and report on that, essentially. Cool. Right. So, what are some of the challenges that we found when we try to apply computer vision models to this task? So, the one was the resolution of the actual object. So, we're trying to detect very small objects in very large images. Sometimes the visibility is severely reduced when the weather is not great, and of course during the night or when the light is bad for various reasons, it also becomes very hard. Right. Cool. Just change track a little bit and give a bit of sort of background on the computer vision techniques that we're using. I think it's always interesting to look at sort of the history of things when we talk about this. So this is sort of the development over the past 8 years of computer vision, in a sense, at least the ImageNet competition, which is quite a famous story. So that was won in 2012 by a network called AlexNet, which were able to improve the results that were before it quite significantly, to the point we don't really care about it anymore. But that was kind of the start of essentially the whole deep learning era, in a way. And with every then subsequent year, there were deeper models and better models and bigger models, until like around 2015, where the model that won, essentially, we like to say it achieved a better than human performance. So it was better at the task than most humans were. After that, it became less interesting, of course, this competition. So that's sort of an ImageNet is a competition of the sort of classic image recognition problem, which is about given an image, what is the actual content of it? Is it an image of a cat or a dog or whatnot? Object detection is related, but not quite the same. So with object detection, we are trying to often find multiple objects in the image and also localize them. So you want to say where they are and what they are. Right? So it's a little bit of a different problem. In the interest of time, I'll go a little bit quicker through this. But the first sort of approaches to this problem was essentially turning the object detection into an image recognition problem. So what people were doing was to use these sliding windows, sliding them across the image, and trying to predict an object within the image. And that actually works okay, but it's very slow because there's essentially an infinite amount of different possible sort of rectangles or areas that can't contain objects in an image. So definitely not if you're looking for any kind of good or real-time performance. It's not what you want to use. Then people went on to be a little bit smarter about it, doing something called region proposals, where they this is one approach to do it. The whole idea is to get fewer of these sort of potential regions of interest from the image. So they'd do some sort of segmentation usually, and then find the sort of connected regions and kind of call that these are interesting regions. We try and predict what objects are in those, and usually you'd then be able to reduce it from a lot to maybe just a few thousand. And one of the early algorithms applying this is the RCNN, which did exactly this. With later versions of that, they also used like a network to actually propose the regions instead of using the selective search algorithm. And this was a lot faster, but still not quite fast enough for real time, because we still have this two-stage approach where you first find the regions and then detect the object. So the next step in the development after that are called single-shot detectors. So these, as the name suggests, do everything in one go. So you have the SSD model and also the very famous YOLO, which stands for you only look once. And as the name indicates, the whole idea is that you only go once through the image, and then you predict everything using regression to find to predict the bounding box. So this works by dividing an image into these sort of grid cells, and then each of these cells have a number of bounding boxes associated with them, and then you use the network to find the ones that are most likely to actually contain objects, and use some sort of threshold to eventually detect them. These boxes are often referred to as anchor boxes, and what it also allows us to do is when you have two objects kind of on top of each other, you can still detect both of them with this approach. One problem you might find is that multiple of these cells can detect the same object. In that case, we use a algorithm called Nonmax suppression, and what this does is to pick the one with the highest probability of being the object, and then it removes or merges that with any bounding boxes that overlap with a significant amount with that box. But so getting back to our application, when trying this on our data, we found that it struggled quite a bit, and we did some pretty extensive error analysis trying to understand why. I think there's two main reasons why it struggled. The one is a very small object. So this is a real image from the wind farm, and there you see there's actually a number of birds in this image, but it's very, very hard to see because they're so small, because they're so far away, that it's even for a human being, it's pretty tricky to identify them as birds. So that's one reason. And also when the object is not against like a clear black background, but rather against the ground, or being obstructed by the turbines, the detection becomes also very, very, very difficult. So that's kind of a challenge. If we look at the YOLO model, then it's the data that it's by default trained on is called MS Coco, which have bird as a class, and it's trained on a lot. These are the sort of images that it's being trained on, which are kind of different from the ones that we're expecting, typically a lot higher resolution. So that's one challenge. What we typically do in the training of object detection models is also some form of data augmentation. So that means that we rotate and scale the images. So it should also be able to detect smaller objects, but I guess there's limits for everything. Like if it's as small as this, it is almost impossible. Another interesting or plausible explanation for confusion is this. So this was an experiment they did trying to understand what the computer vision algorithm was looking at when it was trying to distinguish between wolves and dogs. And what it found was that it was mainly looking at the background, and if there was snow in the background, it was a wolf, and if not, then it was a dog. And so that's just a good reminder that at the end of the day, it's correlations that are being looked at. Right. So this kind of all of this brought us to this idea of using synthetic data, and The reason we wanted to do this is we wanted to move pretty quickly in developing a model. So we like to perform an error analysis. Then we realized usually we need more training data of some kind or another, but we don't really know necessarily have that training data. So how can we get it? And then it was one of my colleagues that said, "Oh, why don't we get?" I know somebody who does 3D modeling for a living, and yeah, I can make very realistic looking images. At first, I was a bit skeptical to the idea, but then started to kind of take to it because it can potentially allow a very rapid sort of iteration of performing the error analysis, generating the synthetic data, training the model with it, and so on. This was the idea anyway. So it turns out this has been done in other fields, like for instance, autonomous driving, where the models are also trained a lot on simulated sort of computer game worlds, and that's you can simulate specific scenario that the algorithm is struggling with, and so on. So the advantages to do that is that it can be a lot cheaper generating rendering data than actually going collecting it. It can speed up your process, and you can cover sort of edge cases that are very hard to find actual data for. So here is some of the data that we had rendered for our application. So it could definitely have fooled me. This was done by a company called Nordic Media Lab, which have been really super in doing that. And interesting enough, they told us they've been doing this for a number of other companies also. So this seems to be something that a lot of people are doing, and it's working. So this is the sort of data that we got from them, and you can see the mask in the other image there. So to train our models, we then have to go and find these pixels, which are color coded in this case. So we find the bounding box and feed that to the algorithm. So these are just quickly some of our results. I don't think they're super interesting at the moment, but it does show that the algorithm is learning. So the simulated data is not just fooling us; it's also fooling the algorithm. It can actually learn what is a bird from it, which I thought was pretty interesting. Like the loss is going down and our metrics are going up as we train it just with this data. So that's a very preliminary result from the experiment, but I think it's at least interesting. I think there's something to it. And yeah, here's I'll just show you a video. Finally, almost out of time, but this is where we're detecting the birds and rendering the video, and you can see it's very hard. It's just a few pixels that they're there, but yeah, cool. So that's the end of this talk. If you interested in this or want to chat more about it, just feel free to reach out. And we are also hiring. So if you thought this was interesting and seems like an interesting applications, there's definitely a lot of challenges that we need to deal with. So if you have a computer vision background or deep learning, and you're looking for a job, feel free to reach out. And we're also looking for some other roles, specifically a data engineer, and also we're looking for somebody, a backend software engineer, to help us build the product that I showed you briefly. So if that's you, feel free. Otherwise, thank you for listening.